Welcome to this math video where we'll explore the tiles method for factoring quadratic expressions, and specifically, why it sometimes doesn't work. Today, we'll look at the expression x squared minus x plus 2 and see if we can factor it using the tiles method. Before we dive into our specific example, let's quickly review what the tiles method is. The tiles method, also known as the area model, is a visual approach to factoring quadratics by representing them as rectangles. For a general quadratic x squared plus bx plus c, the tiles method works by finding two numbers m and n such that m times n equals c, and m plus n equals b. If we can find such values, then our quadratic can be factored as x plus m times x plus n. Let's visualize this with a simple example. Say we have x squared plus 5x plus 6. Using the tiles method, we need to find two numbers that multiply to give 6 and add up to 5. The factors of 6 are 1 and 6, or 2 and 3. 1 plus 6 equals 7, which isn't 5. But 2 plus 3 equals 5, which is what we want. So, x squared plus 5x plus 6 factors as x plus 2 times x plus 3. Now, let's return to our original problem, x squared minus x plus 2. Since the coefficient of x squared is 1, this is in the form we need, where it equals 1, b equals -1, and c equals 2. According to the tiles method, we need to find two numbers m and n such that m times n equals 2 and m plus n equals -1. Let's list all the integer pairs that multiply to give 2. We have 1 times 2 and -1 times -2. Now, let's check if any of these pairs sum to -1. For the first pair, 1 plus 2 equals 3, which isn't -1. For the second pair, -1 plus -2 equals -3, which also isn't -1. So, we don't have any integer pairs that satisfy both conditions. What does this mean? It means that x squared minus x plus 2 cannot be factored over the integers using the tiles method. In fact, this expression is what we call prime or irreducible over the integers. Let's try to visualize why the tiles method fails here. If we attempt to create a rectangle with area x squared minus x plus 2, we simply can't arrange the tiles to form a perfect rectangle with integer dimensions. Although we can't factor this expression over the integers, we can still rewrite it in a useful form by completing the square. Let's see how that works. First, we take the coefficient of x, which is -1, divide it by 2 to get -1/2, and then square it to get 1/4. We add and subtract this value to our expression. Now we can group the first three terms together. X squared minus x plus 1/4 forms a perfect square. X minus 1/2 squared. The remaining terms simplify to -1/4 plus 2, which equals 7/4. So, our final form is x minus 1/2 squared plus 7/4. This completed square form tells us something important about the graph of y equals x squared minus x plus 2. It's a parabola with vertex at 1/2, 7/4. Since the constant term 7/4 is positive, the parabola never crosses the x-axis, meaning the original quadratic has no real roots. Let's summarize what we've learned. The expression x squared minus x plus 2 cannot be factored over the integers using the tiles method because there are no integer pairs that multiply to give 2 and add up to -1. However, we can rewrite it by completing the square, which helps us understand its graph and confirms it has no real roots. This example teaches us an important lesson. Not all quadratics can be factored over the integers, and that's perfectly okay. We have other techniques, like completing the square, to help us work with these expressions. Thank you for watching. I hope this explanation helped you understand why some quadratics can't be factored using the tiles method, and what alternatives we have for working with them.